The next speaker is Bryan Roberts from London School of Economics. And the title of his talk is Weak Interaction and the Curious Little Error of Time. Okay?
Right.
I'm curious to hear what it is.
Thanks. I wanted to start just by talking about a few different kinds of time asymmetry. And so when I was writing these slides, I wrote down, thermal asymmetry, Born rule asymmetry, weak asymmetry, aging asymmetry, Lady Macbeth. You know what Lady Macbeth asymmetry is? That which is done, cannot be undone. The London real estate asymmetry never goes down. But after this conference, so now I changed my list this morning. So now, just at this conference, I've heard all these different characterizations of time asymmetry. This is a really rich concept. We already have time of arrival asymmetry with Jonathan in the beginning, where we had the stop clock that picked out a preferred direction in time. We've had clock asymmetries with Lorenzo, entanglement asymmetry. We saw a shrinking W-star algebra asymmetry, if we think of a net of W-star algebras for quantum mechanics. Cosmological asymmetries today. Nicolas had free will and choice asymmetries, but also boring and creative time asymmetries. We had moving now asymmetries with Tony, and knowledge asymmetries. We saw causal Markov asymmetries, many interesting notions of asymmetries. And probably I even missed some. I don't know, can you think, is there some that I missed? Or I got them all. Maybe I got them all. So there's a lot of different concepts of time asymmetry. And I guess I'm the first one now to add this focus on weak asymmetry. So I'm going to talk about asymmetries in time and the weak interactions. And so this sort of starts with this interesting paper of a guy who was a young, new, fresh PhD graduate starting a postdoc at Columbia University, and his name was Steven Weinberg. And he wrote, in analyzing the recent experiments involving p-violation in the weak interactions, he was interested in just how much evidence there was for CP invariance or CP violation. And his conclusion in this paper is that CP invariance and the given CPT symmetry, the equivalent time reversal invariance, that these are very, very likely. It's very, very difficult to understand the physics in any other way. And so he says here, at the end of a long argument I'm not going to go through, but that sort of, in particular, that these two decays, which would be T violating and CP violating, and for them both to be very, very small, he suggested, because they were at least small and maybe zero probability, would be very unlikely. So the most likely way to understand this is to think that CP invariance holds. And lots of people thought this at the time. So here's James Cronin reflecting back on this episode. And he says, look, it just seemed evident that CP symmetry should hold. Why? Well, people are thick-skulled. We all are. Even though parity had been overthrown a few years before, one was quite confident about CP symmetry. And then, of course, you may know, it came as a great shock in 1964 with the discovery of Cronin and Fitch that the world is CP violating. And given CPT invariance again, this means that nature makes a difference between the past and future, even at the most fundamental level. And you hear this a lot, it came as a great shock. People describe this historical episode that, we were really, really surprised. In the parity episode, you might know that Feynman lost $50 on a bet because he thought that parity would never be found to be violated. So he lost $50. And so people often talk about this shock. But it's funny that in practice, when you open a textbook, or even you read a philosophy paper on the nature of the arrow of time, that this shock isn't reflected today, okay? So maybe there was like this initial shock, but I guess, most of us don't walk around and feel that shock. Goodness, time reversal is reflected in nature. It's kind of like, I was trying to imagine, like, what is an analogy? And it seems to me it's sort of like when you see somebody like a chainsaw juggler. There's a chainsaw juggler in London. And when you first see him, you're really shocked at this guy. Like, what is he doing? He's half naked juggling chainsaws. And then you immediately forget about it. You go home. You never think about the guy again. And so this is normally what we do with T violation in the weak interactions. Wow, that's really neat and cool. And then now we bracket it. And by bracket it, I mean, well, so you look at a typical textbook. For most intents and purposes, we say, all right, we're just going to ignore T violation. Perfectly legitimate to do so in Messiah. There's no real treatment of weak interactions here. So we postulate that the theory is reversible with respect to time. But similarly, for philosophers who analyze the nature of time's arrow. So here's Hugh Price in the book Time's Arrow and Archimedes' Point. They say things like, well, the best strategy to understand time's arrow is to sort of ignore these strange neutral kaon decays and the weak T-violation phenomenon. And some people have even gone further than that and said that maybe all this ignoring is actually justified, that maybe someday we're going to find that these arguments don't really work anyway, that the experiments we have really provide evidence of T-violation, they might be bogus. They rely on things like the CPT theorem, and maybe somebody doesn't trust the statement of of CPT invariance. So here's Horowitz claiming that these are implausible arguments. So my main goal today is to argue that we have these three templates for T-violation, two of which have been pursued experimentally and confirmed, and they're not likely to go anywhere either. So as a preview, the things I want to talk about are this Curie approach to T-violation, the Kabir approach to T-violation, and this Wigner approach, which I actually cut also this morning. I think the talk was too long, so we could talk about it in questions period if you want, but I'll just say some brief remarks about this. The first one involves comparing unitary symmetries of in-states and out-states and then applying the CPT theorem. Some people call this the indirect approach. The second approach is to look at the amplitudes of decay modes and then look at the time-reversed decay mode and compare the two. And this one involves looking for a special property that we've not yet observed in fermions, which would be characterized by a certain non-degeneracy in the energy spectrum. But in particular, the way it plays out, the example that people look for is what's called a fundamental electric dipole moment, where instead of having an electric dipole given by a distribution of charges, you imagine you have just one fundamental particle, which would be spherically symmetric, and that it had an electric dipole picking out a preferred moment. And these turn out to be T-violating, and they turn out to, this is the sort of framework that those fit into. Anyway, so these are sort of templates. Now you're going to notice here, I'm really zooming out a lot, and I want to just look at the structure of our arguments for time asymmetry from this sort of bird's eye view. So I'm not going to go deep into the CKM matrix and the theory of weak interactions that underpin these things, except I'll remark a little about it. And mostly I just want to understand the structure of our arguments for T-violation and how they connect to the evidence. And I want it to be fun too, all right? Because I feel like part of what keeps people from understanding T-violation is that it seems so exotic and it seems so far away. And so when I give this talk to philosophers, I like to give this picture. It's going to be three merry roads, we'll kind of explore this one, and it'll be friendly. So the first one is, I called it Curie, the Curie approach. And it's not like Pierre Curie was involved in weak interactions, but he was involved deeply in the analysis of symmetry. And then this was really in the discovery of the piezoelectric effect for the first time that he realized this seems to be this pervasive symmetry principle that can be applied in many different physical contexts. And the principle he wrote down was that when certain, this is now just kind of vague physicist language, that when certain effects show a certain asymmetry, this asymmetry must be found in their causes, which gave rise to them. Many have formulated this in a somewhat slightly more precise way to say something like this, so interpreting Curie now. So he's saying symmetries of the cause give rise to a symmetry of the effect. And so, we're going to now, I don't know if this is, the only way to interpret cause, but one way to understand cause here is to say, well, what gives rise to the motion is two things. We have this dynamical evolution and we have an initial state. So it's kind of like the cause. And that if the symmetry applies to both of these things, so I have a symmetry of the dynamics and I have a symmetry of the initial state, the principle is supposed to tell me that that must then lead to a symmetry of the final state too. And now you want to say it even more precisely, so we're going to get there, okay? And I'm going to show you along the way now how we're going to turn this into a way to understand symmetry violation. So this isn't now going to be how Curie intended this, but you'll see it's closely related. So we'll say now, if a law is invariant under a symmetry, then the initial and final states should both either share or both fail to share that symmetry. So that's now the statement of Curie's principle we want to work with. Now this statement, we'll just put it in contrapositive form. It has this interesting, helpful-looking form, okay? Here's an equivalent statement. If the initial and final states do not share the same symmetries, then they are not symmetries of the laws of nature. So really, you can view Curie's principle as a trick, as a tool for understanding when you have symmetries of the laws of nature. If you find it hard to tell, well, you can just look at the initial and final states and check whether or not they share a symmetry. So trick in hand, we'll formulate this just a tiny, now finally a little bit more precisely again. Suppose we've got a unitary symmetry U on a von Neumann algebra or a Hilbert space of vectors or whatever you want. There's various contexts this can be formulated. Unitary symmetry and a non-zero decay amplitude, psi in, psi out. So this is thinking of S now as an S matrix. And we suppose that this satisfies either one of these two things, okay? In symmetry but not out symmetry is the first possibility. So we're saying that I apply my unitary symmetry to this in state and it leaves it alone. Nothing happens to it, okay? So it's preserved by the unitary symmetry. But we don't get that on the out state. So say it reverses the phase of the out state. Or suppose that the reverse happens, that it preserves the out state but not the in. So in but not out, or out but not in. Then we have U symmetry violation in particular. So this implies that the laws are symmetry violating. Yeah. No, it's just an easier argument this way, yeah. Yeah, I mean, the proof is like 3 lines this way, and it's like 6 lines otherwise, I guess. Yeah, so this is the first statement that could be helpful in seeking T violation. So in a sense, all we're trying to do here is, take some interesting, well-motivated principle and come up with a way to test whether or not the laws of nature, and in particular unitary evolution in an interesting quantum system, is symmetry violating. And you notice here I said unitary, so that's important. This argument doesn't work if it's anti-unitary, so I'll come back to that. So now we want an example of that. Here's going to be an example of that. We're going to look at an in state that is a neutral kaon, a long-lived kaon, and we'll look at an out state that's a pair of pions. And it happens that these two states don't share the same symmetries under the CP transformation. CP preserves the pion pair, and it reverses the neutral kaon. So if we were to detect such a thing, this interaction would be T-violating. This decay would be an example of a T-violating S matrix. And that's just what they did. So here's James Cronin hanging out in the Brookhaven National Laboratory in New York. They said they had to use this kind of old-style, scintillation chamber where you watch for a long time as like little particles ionize in the box of gas. And they take tons and tons of pictures of this thing. And this is one, so that to give you an idea of the sort of thing they were looking at, they had to look at thousands and thousands of these pictures. This is like a delayed reaction eureka moment, where after several months of analyzing these things, they found that indeed these decays do happen with a non-trivial branching ratio. So we have these neutral kaons decaying into 2 pions, and so we have CP violation. And now we're coming back to T violation. All right, so given CPT invariance, if we presume that this interaction is also CPT invariant, CP violation is equivalent to T violation. So we get time asymmetry out of this. And it's not implausible, really. I mean, all known interactions, as best we can tell, seem to be CPT invariant. And there are formal arguments that suggest that very, very general classes of interactions are CPT invariant. They often make use of things like Whiteman fields and Hogg axioms, and then they presume Lorentz invariance, and you get this CPT invariance coming out. But it's not, beyond challenge. This is, of course, challenged in extensions of the standard model, where you start relaxing some of those assumptions. Now, coming back to the unitary thing, so you might think we can do one better and apply the same Curie thinking and get a direct fix on T violation. Suppose you're uncomfortable about our access to time asymmetry in the weak interactions through this indirect argument. You want to somehow use the Curie argument and come up with a direct experiment for T violation. It turns out you simply can't use that argument. You have to invent a totally different argument. And you can try and write it down. It takes just a couple of lines. You can see that the statement is simply false. I mean, I could just say it. If you think of an example like a classical harmonic oscillator, and is described in a phase space but with variables q and p for position and momentum. And so I've got this thing bouncing back and forth. And just take a starting state where it's got 0 momentum. So it's stretched all the way out. That's its initial state, 0 momentum, but it's stretched out of equilibrium. And now I let the bob fall back in. I'll detect so that's an initial state that's time reversal invariant. Okay, I reversed, I apply time reversal, doesn't change position, doesn't change, it does change momentum, it reverses momentum, but this is a state that's stationary, or it's not moving, so it doesn't do anything to it. But all later states, right, as it moves, they do get changed by time reversal because the momentum gets reversed. So there's tons of interesting examples of initial and final states in the harmonic oscillator, which aren't both time reversal invariant. And yet the harmonic oscillator is, it's a canonical example of a time reversal invariant system. It's manifestly time reversal invariant. And you just check the Hamiltonian to know. All right, so this thinking doesn't apply to time reversal. Second remark is that, but this thinking is very, very general. So I wrote it down just to be, semi-precise in terms of unitary symmetries and S matrices. But you don't have to express the statement that way, okay? The structure of the statement and the structure of the argument requires little structure from quantum theory, really. You can sort of say things like this, that just take any set, P, just a set, and I'll take, instead of an S matrix, I'll just take a bijection that takes me from one copy of the set to another. And then I suppose that I have, U now is going to be a mapping on the P ins, or there'll be a version mapping on the P outs. But otherwise, I sort of say the same thing. Then you can make the same argument. So there's very, very little going on here. You're sort of just using bijections on sets to make the argument work. So in that sense, it's close to, and Abby Ashtekar has a talk about this. And another example I'll show. Good. All right. So in that sense, there's very little structure in this expression of T violation. So now the other expression of T violation I wanted to talk about is due to this guy called Pasha Kabir. Or really, I think it's an older principle, but in the context of weak interactions, he suggested you could test for T violation this way in 1968 and 1970. And his statement, is also simple to say in English. Now, again, talking in the language of quantum mechanics. Suppose the amplitude of it, I've got a decay mode, A decays to B, and I'm going to consider the time reverse decay mode. So time reversal of B decays into time reversal of A. And I'll look at the amplitudes of those two with respect to whatever the scattering matrix is. And if those two amplitudes are different, the original and the time reversed amplitudes, that's an example of T violation. So T violation can't change those. That's the principle anyway. And you can say this a little bit more precisely if you want as well. Take psi in to psi out to be some non-zero decay mode. And we describe the time reverse like this. Time reverse of psi out, time reverse goes to time reverse of psi in. And we just compare these two branching ratios. If they're not equal, then one can show straightforwardly that we have T violation. That's another, again, it's a very easy sort of argument. But it gives you a trick, okay? So now we have another trick. If we can compare a branching ratio to the time reverse branching ratio, now we have an easy access to whether or not the laws governing this interaction are T violating. And there turn out to be these very interesting, unusual properties of neutral kaons that make that easy. And the property is this thing called oscillation, where you start with a kaon, it decays into an anti-kaon, and then the anti-kaon goes back and decays into a kaon again. A very unusual and exotic property. And it's responsible for a lot of the unusual features of the weak interactions. And these states, by the way, are strangeness eigenstates of plus and minus 1 by convention. All right, so now if we were going to look at this example, we'd look at a kaon goes to anti-kaon amplitude. We'd compare that to the time reversed amplitude, which turns out to be the anti-kaon to the kaon amplitude again. So we don't even need the T operator in here as a sort of nice thing. It's equal to this quantity. And if we find these two amplitudes are different, if there's a different decay rate for these two modes, then we have an example of T violation. So that's what Kabir's principle says, and that's what's a mathematical fact about quantum theory. If the amplitudes differ, then the interaction's T violating. So it's nice. I mean, now it doesn't make it easy to perform the experiment, but I mean, in principle, the fact that these oscillations exist make it a little easier to check whether or not you have non-trivial T violation. And so, you just need a place to do this, and Switzerland turns out to be a great place. So you just go over to CERN at the C-Clear experiment, and this is where in 1998 they set this experiment up, and found that indeed these two amplitudes are different. And so the title of the paper is, I think, something like the first direct confirmation of T violation. Direct in the sense that we no longer have to use the CPT theorem to make this argument. It's using Kabir's principle. Now, so this is an active area of investigation. I mean, so I'm going to talk in a second now about why some of why that is. Recently, just in 2012, T violation was detected in another sector, in the B meson sector at SLAC. And a hot thing to do now is to try and figure out a way to formulate an experiment that would test for T violation with neutrino oscillations. And often these are similar sort of, they're similar oscillating particle-antiparticle phenomena that make this a plausible way to detect the phenomenon. So these are all following up on Kabir's principle, really. And interestingly, it's just a slightly different way of arguing than Cronin and Fitch. But it turned out to be crucial to get a handle on direct T violation, direct detection of T violation. So, and then here too, and this is just like a little bit more complicated to say, but the Kabir template is also much more general than standard QFT. So when I first looked at this, I sort of thought that there were, things like linearity and unitarity were playing into the argument of this proof of Kabir's principle. And you sort of, you can use them when you prove it. But it's just not necessary, it turns out. And Abby Ashtekar pointed this out to me. He has an archive paper describing this in more detail. He's interested in particular, nonlinear expressions of quantum theory. He's got a bunch of work on so-called Kähler manifold approach to quantum theory. And so he said, suppose I don't have I don't really have a linear structure for quantum theory. Suppose I don't have anything that is truly like unitarity. Can I make the same argument? And you can. You replace the inner product with a sort of this formal thing called an overlap map, which fits into a broad class of theories. So Ashtekar wrote down like this. I guess this is not so meaningful. We don't have to dwell on it unless you want to in questions. But this statement was that we're now again just looking at a set, and we've got an overlap map, which is sort of standing in for an inner product. So it's not really an inner product. Well, the normed inner product. It's not really a normed inner product. But you can make a similar argument. You see, you're doing something like saying, if the overlap map is not the same for the time-reversed interaction and the original interaction, then you get T violation. So these are them, right? These are the merry roads to T violation. They're straightforward. You have CPT plus Curie's principle, in which we compare decay products. And we had the neutral kaon going to the two pions. We have Kabir's principle, which compares transition amplitudes for particle 1 to particle 2 in the time reverse. And then we have this Wigner principle thing, which is to observe non-degeneracy. And maybe I guess the only remark I'll make about this, unless we could talk about it more at the end, is that this came from a novel proof of Kramers degeneracy. So it turned out to be important when we were investigating very low refrigeration techniques in the beginning. People were using magnets, still often use magnets to create very, very low temperature environments. And so what you wanted to do was understand, in particular, the electron degeneracy of different kinds of paramagnetic salts, so you could know what would be a better way to create low temperature magnetic environments. And Kramers came up with this this fact that seems obscure unless you're in that context, which is that for a wide class of electron systems or fermion systems with an odd number of fermions, you always have degeneracy in the energy spectrum. You always have orthogonal energy states which have the same energy eigenvalue. And Wigner is the one who realized, so the novel proof is that it turns out you can just prove this in like 3 or 4 lines, as you do in standard textbooks, from the assumption of time reversal invariance. Right? So you probably have seen this calculation before a long time ago, maybe. You presume time reversal invariance, presume you have a single fermion or an odd number of fermions. And I guess the relevance of that is that for an odd number of fermions, the time reversal operator has this funny property. You'd think that normally a reversal is something that, you apply it, I reverse the orientation of the bottle once, and I do it again, and it's back to where it started. At least that's how you think. And it's true up to phase in quantum mechanics, but you might remember again that in fermionic systems of odd numbers of fermions, this is equal to -1 times the identity operator. So that's where the sort of odd numbers of fermions things comes out. So apply time reversal twice, you pick up a phase. Just like you apply a single rotation through 360 degrees to an electron, and it's not back to where it started until you rotate it again. So we apply time reversal invariance, and we derive this electron degeneracy. And it turns out now we do the same sort of thing as Kabir did, as we did with Curie, and we just look at the contrapositive. And what this means is that for certain kinds of fermion systems, if we were to discover non-degeneracy, that implies T-violation. So a certain sort of, that's supposed to be evidence that a certain sort of matter, a certain sort of fermion in particular, can give you evidence for T-violation as well. So, but I won't talk much more about this. And we've never detected T-violation in this way either. All right, so here's the sense in which these templates are here to stay. Just to review, we didn't really need linearity or transition probabilities or unitary dynamics or Lorentz invariance to ground the way T-violation comes out of these experiments. At least from the bird's eye view, the kind of skeletal structure of these arguments is more general than that. And so here's Ashtekar saying the main strength of the more general perspective presented here is that it broadens the reach of Cronin and Fitch and Seepler experiments enormously. So the last thing I wanted to talk about is this puzzle now. So this is kind of, after we've viewed the merry roads, there's an interesting puzzle about T-violation, which is to do with its small size. Yes?
But before you go to this, so before you continue, so you use this time reversal operator, because you said that one particle is the time reversal of the other. How do you define that in general terms if you throw out of the window unitarity and Lorentz and whatever?
Well, sometimes you do.
What does it mean, that T?
Yeah, that's a good question. I am a fan of arguments like the one that was given yesterday, in which you try and think as best you can about the general arguments for anti-unitarity or for unitarity. So there are sorts of arguments that are given in the context of quantum theory that would establish what it means for time reversal to transform one state to another state. So why is this T and not something else? There should be a physical reason. But I don't think that you can do it just in a vacuum. I mean, of course, it depends on a case-by-case basis. So, I mean, the simple answer is, you ask, why doesn't the physics of strong interactions and Lorentz invariance and all that give you, that's where you get the meaning of time reversal in the first place. And that's true. But at least the abstract, again, this is sort of taking a bird's eye view on the sorts of arguments that ground time reversal in experiments, time reversal violation in experiments. And those arguments don't depend on those structures. So that's my main claim.
So how do you know that the antipion is related to the pion by time reversal?
Well, that turns out to be, yeah, with no theory for that, you simply can't say. Yeah, you're right. You do need some theory for that. That's true. Yeah.
That's the same with the other symmetries as well, right? I mean, the first one you presented doesn't hold if you have it's not a unitary evolution. It can start in some state which is not respecting, which doesn't respect X translation invariance, and then it just kind of goes
Yeah, so, but then the law describing that would be symmetry violating. I mean, that's the sort of thing. So there's three things. There's the symmetries of the initial state, symmetries of the final state, and symmetry of the dynamical evolution, where what you mean by that is, if a given trajectory is possible, is a transformed trajectory also possible?
No, but I think if you don't have a unitary evolution, then that's not the case. You can have just because the Pauli distribution will be uniform over all space, so it respects translation sense, initial state.
I'll have to think about the example. Yeah, maybe let's talk more after. So you're saying this is a violation of the Curie principle without unitarity. I'll think about it more. I mean, but what I suspect is, that it subtly depends on how you formulate these laws, but.
It's like the maximum mixed state respects all symmetries. So if you take an evolution law which goes to the maximum mixed state, you will have it.
Yeah, and the question is, can one formulate such a symmetry such that it is, you have to keep it time reversal invariant, so, or rather, oh, I see. So yeah, isn't the argument then? Yeah, it's supposed to be time reversal invariant. So to violate the principle, you need that evolution to be time reversal invariant, and you have an initial state which is not symmetric under time reversal, and a final state which is symmetric under time reversal. Is that the sort of point of the example?
Yeah, or even any symmetry.
Yeah. Okay. Yeah. Any symmetry. Yeah. Yeah, I don't know. I mean, it's such a simple mathematical fact, the Curie principle. I mean, we can look at it after in the context of the set structures, and you can show me what's going wrong. All right, so the last thing about the puzzle of small size, I guess, yeah, and I wanted to mention this because it's another thing that's sort of not talked about that often, but has interesting physical and philosophical consequences. So the reason they had to look at thousands and thousands of the horrible slides, Cronin and Fitch, is that this decay only happens in 1 out of every 500 decays. So it's a very, very small branching ratio. Now, that doesn't mean it's not important. So again, if you're thinking about unitary evolution as just pushing through the universe right now, this is a very, very pervasive tendency. It's a signal that can't be ignored. It's just a small branching ratio. Example of a signal that might be very, very small but might have a large effect later on. You have a hole in your boat, so you don't want to just ignore something because it's just a very small tendency. It can lead to a big effect. So a philosophical question is why is this thing small? Why not large? Or why not zero? And to kind of pump why this might bother you, parity violation and charge and C violation that came out of the Qin-Cheng Wu experiments were both examples of maximal symmetry violation. On the other end, strong interactions don't appear to be T violating at all, so like zero T violation. And so that seems weird. So, I mean, so why is it just a little bit in the case of weak interactions? Just a small amount of T, just a little bit of T violation. And so, I find it hard to express why exactly this feels puzzling. But maybe one way to put it is in terms of this boat analogy again, another boat analogy. You get on a boat and you see there's no life vests at all. You're like, well, they don't care that much about safety. They just don't have life vests. And you get on a boat and there's a life vest. There's a lot of life vests. Everybody has a life vest, and that sort of makes sense to you too. They care about safety. But you get on the boat and there's just like 3 life vests, or just 1 life vest. You sort of want to understand why that is. Maybe the captain was like, yeah, I'm going to make sure I don't. I know this is a rough road ahead. I'll bring a life vest for myself. Or there might be some mechanism underlying why there's just this very small effect. So often these small but non-zero occurrences have interesting explanations. Now, an interesting physical application, if there were a nice explanation, is help towards understanding the baryon asymmetry in the universe. That when we look, we see a whole lot of galaxies made of baryons, and we don't see a whole lot of galaxies made out of antiparticles. And that's funny. And so you could ask where this asymmetry comes from. And people have done this. we looked in the very early universe distribution of particles, and it seems to be the case that there is a very small difference in the particle versus antiparticle distribution in the early universe. Very small, in the order of 1 billion and 1 particles to 1 billion antiparticles. And so the idea is, and this idea comes from Sakharov in 1967, and many people followed up on this, that we might be able to then explain, so if we can get to here, and you imagine somehow evolving this and ending up with a large baryon asymmetry, all we really need to get to here is some kind of nice interaction that's grounded in fundamental physics that gives rise to a baryon asymmetry, like CP violation, or T violation in the context of CPT invariance. But you still have this question, I mean, once you've done this, about why CP violation is small, okay? A small amount of CP violation would explain the small early universe asymmetry. But why is a CP violation small? If we could answer that, we'd go a step further towards understanding the baryon asymmetry in the universe. But I'm afraid I don't have a good answer to that. It's something I'm wondering about now. And I'd just like to note at the end now that this same question was driving many of the arguments in the beginning about CP invariance. So this is going back to the Weinberg article from the beginning. Weinberg was looking at, he had this methodological thought that when we wanted to assume, we wanted to understand the best explanation of why there seems to be a very, very small or possibly zero, something we haven't yet detected, decay mode which would be CP violating. So why are these decay modes small or zero? And methodologically, he sort of thought that it's a better explanation to suppose that it's zero. And many people at the time said, look, it's just much more plausible to say that it's zero than it is to say that it's just very, very, very small. And so they took what they thought was the simplest explanation and presumed these models were CP invariant and built a lot of models of weak interactions on this basis. And this was an example in which the simplest explanation was wrong. So word of warning, it's not always right just to be simple. But that doesn't, it doesn't solve the methodological question. So, his question was really never answered. Why is it then that, he says here literally, the phase relation here would fall, so you've got multiple modes here that don't seem to ever occur. This phase relation would follow from CP invariance, but it's difficult to understand on any other basis. It's simply difficult to understand if there's just a very small effect. Why else would there be such a small effect? And this was never really explained. Now, of course, the theory was developed, and we write down now an interaction matrix that describes the charge current transformations that give rise to these interactions. But the parameter itself, the fact that the parameter is small, it's a free parameter. It's just determined by experiment. So we don't really have an explanation of that. Not everything requires an explanation, of course, but this puzzle seems, at least to me, to be one that demands one. And that's all I'd like to say. So, thanks.
Okay, there's still time for questions. Jonathan? Huh?
Maybe just regarding Sandy's question, is another case, I guess, maybe I can make so it's about, if I understood correctly, about making the initial and the final states. How do you know what the T reverse looks like if you don't know that it's unitary?
Yeah.
Can you not just say that that's just a kinematic reversal, that you just, when you say what the initial state is and what the time reverse state is, you're just doing the kinematic reversal, and so you don't need to know the dynamics?
I see. Well, yeah, maybe I didn't understand the question then. Yeah, that is what I had in mind. So the way I understand, an argument was given yesterday too, of this character. So you often understand or the meaning of time reversal by thinking about the kinematics, which does depend on the underlying physics. But there's some stuff that you can sort of argue in the abstract. So an example of something you might say is that the meaning of time reversal shouldn't depend on position in space. You might say that the meaning of time reversal is homogeneous. And if you say that, what you're really saying is that the generator of so if I take these, if I time reverse the spatial translation operator, I should get back the same thing. Or put it as equivalent to say, if I spatially translate the time reversal operator, I get back the same thing. And that implies that momentum gets reversed. So if momentum is the generator, time reversal is this anti-unitary operator, as we learned yesterday. So as you pull that t up into the exponential e to the I sp, it reverses I, and so this requires p to be reversed. So in short, the argument is, assume space is homogeneous, you can conclude that momentum should be reversed. So that's a sort of general kinematic arguments that can be given to understand some things about the meaning of time reversal. So time reversal reverses momentum. And you can give similar arguments to understand time reversal in the case of spin and other things. Thanks.
Any other question?
You didn't really say anything in the end about whether people who are interested in these other areas of time, like Q Price's book or whatever, like, are they justified in ignoring this?
Well, I think if you want to understand the arrow of time, then no. It's a pervasive feature of time. It's a pervasive arrow of time, and at least in some senses, it's a very general effect that doesn't look like it's going anywhere. One of the things that Hugh worried about, though, is how it's related, how this arrow is related to what he called the thermodynamic arrow. And there may not be I don't know really of an interesting relationship there. Thermodynamic arrows, being one that's supposed to really come out of special initial conditions. This is an asymmetry that's truly an asymmetry of the fundamental laws, so maybe it's not obvious to me there is a relationship between the two.
Well, just to continue with this, you can always amplify a small effect, yes? You can connect the price of stock to these decays, so then it will go in one way. So you can always...
Yeah, I can have a big... Yeah, exactly. That's a great example. I should use that instead of my boat analogy. Yeah, a small effect can be hugely amplified, especially over a long time.
I guess you want to impose that even this small effect could be then related to other asymmetries via amplification.
Yeah. Oh. Yeah, I didn't mean to say that it was just a small size, but I guess it's not obvious to me if we understand thermodynamic asymmetry to come out of there being very special initial conditions that correspond to a low entropy state, then this is a different sort of symmetry in that it's built out of the fundamental dynamical law, not out of anything really to do with the initial conditions. And so that connection is what I don't really know how to make.
Okay, so thanks again.
Thanks.